Hi class. Today we're going to be discussing applications of derivative. I'm very excited about this lesson because we have spent a lot of time learning about how to take a derivative, what the derivative means in terms of the graph, but we haven't talked yet about real-life applications of derivative. So that's what we'll be doing today. This is section 3.4 in your book. And you'll have to excuse me using the pen at my desk is not as easy as doing it at the smartboard. So my learning curve may be a little slow. I'm going to pick a thicker color. I don't know where my black pen went. Okay, so derivative is the instantaneous rate of change of a function at a point. If we consider derivative in terms of motion, motion can be summarized with an equation, and let's call it a y equals equation. And that can tell you the distance equation, which is also called the displacement. So you will recall back a few weeks ago when we were talking about measuring the motion of a falling object, we wrote that equation in terms of y equals 16t. So 16t squared. So that particular motion equation was in terms of time, and the y value represented how far that object had dropped in the given amount of time. So if you plugged in t equals 4, you got how far the object had dropped in 4 seconds. Now think of what rate of change of motion would be. Well, if this is in terms of time, the rate of change of motion is the change in displacement versus change of time. In other words, it is the velocity. And since it's the rate of change, the way we get rate of change is by doing y prime. So y prime is the instantaneous no, I'm forgetting the t. Let's back it up. Wow, that was a big backup. Instantaneous speed, or the instantaneous velocity at a point t. The units of this are going to be a distance over a time. All right, so this unit is simply the distance. If you take the velocity, take the derivative of y, and you get the units of distance over time, and that represents the instantaneous velocity. Now, you have velocity, which measures the rate of change of the motion. Now, what's the rate of change of the velocity? Well, we call that the acceleration. Whoa. Maybe I should use a highlighter. Okay, so here's the acceleration. And that is given by taking the second derivative, because you're finding the rate of change of the prior equation. So this is the instantaneous acceleration of the object. instantaneous acceleration. Okay, and our units of that, okay, again, we had, let's say, feet per time unit, so feet per second, feet per hour, depending on what we're talking about. The units of acceleration are distance over time. So in other words, distance over time squared. And that is our unit of acceleration. So it's very exciting that we can take this math concept, derivative, and apply it now to Newtonian physics. Newton was the person when it came to this sort of physics, the physics of motion and of calculus, and it was because the two things are so intimately related. Let's take a look at the equations we talked about last time we do this. Oh, that's supposed to be y. Bummer. Okay, here we go. Y equals 16t squared was the distance a falling object traveled. Okay, so distance a falling object traveled. And if you recall the units, y was the feet and t was in seconds. So we could calculate how long it took something to fall. We could time how long it took something to fall, and then we could calculate the distance that object had in fact fallen. If you take the derivative of this, y prime, using the power rule, we get 32t. You multiply 2 times 16 for the 32, and then bump the power down by 1. This, in fact, is the velocity equation. It's the instantaneous velocity in our units, feet per second. So v of t, that's another way to note this, is 32t. So if we want to find the velocity at any one point, we simply plug in that time value and we can calculate the velocity of that falling object at any point in its journey. Okay, and again, our units are feet per second squared because we differentiate this, we take the derivative with respect to time, meaning we treat t as the variable of differentiation. All right, so that's velocity. Now, let's consider taking the second derivative. So I take the second derivative of 32t. Well, what is the slope of a line that's 32t? Or you can think of it as 32x. It's just 32. Or we could think of it as applying the power rule. So this is the acceleration in feet per second per second. So those units we write as feet per second squared. I'm going to move this jobber up here, try and hide it a little bit. Okay, so this is the acceleration in feet per second squared. So, oh, need my pen back. All right, so my acceleration with respect to time is simply 32 feet per second squared. Interesting, huh? This is a constant. It doesn't change. It doesn't matter where you are in the journey. The acceleration is always 32 feet per second squared. So what that says about our falling object is that it is always increasing in speed. Every second it falls, it gains 32 feet per second of velocity. Okay, so this object, the more it falls, the faster it gets because it has this positive rate of acceleration that doesn't change at all. So it's constantly speeding up. This, in fact, is a constant. It is called g because it represents the rate of gravity on a falling object. Clearly falling because gravity has effects on it. So this is G. So G is 32 feet per second for any falling object. Sorry, feet per second squared, which if you're working in a physics class, they have you work in meters more than anything else, the metric system. That's 9.81 meters per second squared. Okay, those are the same thing, just with the units converted. And this is a gravity constant. If you ignore wind resistance, any sort of particulate matter in the air, and the object is falling in a vacuum, this is the rate of acceleration in which it falls. So that is our gravity constant. And you can see, if we look at how this developed, we started with our displacement equation. We took the derivative, that's the first derivative, to get the velocity, and then we took the second derivative to get our acceleration. Okay, and these are for falling objects. Okay, not for any object, only for falling objects is the force pushing that down the same, at least on this planet. All right, so that's our gravity constant in free fall. So I should probably write that down. That's in free fall. Whoa. Let's undo. That's kind of messy. In free fall. Sorry, I can't write very quickly. All right, so we're going to use these facts to help apply the concept of derivative when it comes to physics. We're going to do some economics, some engineering problems, but they are quite exciting. But they're all, at least the physics one's going to be based upon this principle right here. The derivative of distance is velocity. The derivative of velocity is acceleration. Very exciting things. So we are going to go through one or two book examples. So I'd like you to open your textbooks to page 129. And I'd first like us to look at problem number 2. And I'm going to walk you through that together. So get out your books. Share with a partner if you don't have one. There's some on the bookshelf if you absolutely can't find someone's to look off of. But I'm going to get started, so get yourself together. Here, let me move this down. Okay, so the equation, let's write in blue now. The equation for this, S of t, gives the position, so in other words, how far this particle is from 0 of a particle, in terms of a quadratic function t squared minus 3t plus 2. Now, the very first question says find the displacement. So in other words, find how far the object has gone during the first 5 seconds. The key word in A is during. During. Okay? You don't plug in 5. Well, you do, but that's not all you do. You do other things. So the displacement during the first 5 seconds. Okay. So you have to consider, this is what everyone forgets, you have to consider where the object is at the beginning of the journey and at the end of the journey portion that we're looking at. At 0 seconds, is our object on 0 on the number line? No, our particle is not. S of 0 is not 0. S of 0 is 2. So we are at 2 meters. Okay, 0 squared minus 3 times 0 plus 2 is 2. Now at 5, that's 5 squared minus 3 times 5 plus 2. So 25 minus 15 plus 2 is 12 meters. So you have a particle, and picture this little guy, or girl particle at 2 on the number line and then traveling to 12. So what is its net displacement? It is not 12 meters, although on the test you guys will tell me that. It is 10 meters, okay? Because it has moved 10 meters net displacement in the first, during the first 5 seconds. Okay, so that is part A. Part B says find the average velocity. Now the key word for part B is average. Averages can be found without doing calculus. Do not take the derivative. Okay? That's a do not. Emphatic do not. Because you're finding an average. You can find an average without a derivative. It's actually very easy. The average velocity is the change in position over the change in time. Okay? Just like the average slope is the change in y over the change in x, the y value representative is s of t. Okay? So it's the change in our s over the change of t. Well, during the first 5 seconds, how far did we go? What was our change in position? Hey, we can look at part A. It's 10 meters. All right. In the first 5 seconds, how much time has gone by? Well, 5 seconds have gone by. So our average rate of change, aka our average velocity with these values, is 2 meters per second. Please note I did not take a derivative. Okay, so that's the average, the change in position over change in time. Okay, don't forget that. Part C, now we get to some calculus. Instantaneous velocity. Okay, the instantaneous velocity is found by taking the derivative of the position function. Here is our position function, s of t. So now differentiate s prime of t, which is also written as v of t, because the derivative of position is velocity, is given by 2t minus 3. And the problem asks for the instantaneous velocity at t equals 4 seconds. So v of 4 equals 2 times 4 minus 3, which is 5. And again, units are very important. 5 meters per second. So it's not bad to point out this particle must have been moving quite fast at 4 seconds, because look at what the average was right here. This is the average 0 to 5 seconds. The average velocity was 2. And here I'm at 4 seconds in that interval, and my velocity is over double that. So that thing is really moving at that point. All right, so we have both the average velocity over a period of time and the instantaneous velocity that's at 4 seconds. Okay, part D asks you to find the acceleration. Well, based on what we just discussed, acceleration is the derivative of the velocity graph. So I want the acceleration at t equals 4 seconds. So I need to find an expression for acceleration. Well, let's take a look. This here is position, or displacement, or distance, however you want to consider it. This here is velocity, and they are related by taking the derivative. The last thing is the derivative of the velocity graph. So, the derivative of the velocity graph is 2. The slope of this line at all points is 2, or you could consider that with the power rule. So the acceleration in terms of time is 2. So it's kind of a trick question because they're saying find the acceleration at 4 seconds. Well, the acceleration at any point in the journey is 2. 2, 2, 2, 2, 2, 2, 2. It's always 2. Whoa. Okay, let's redo that box. Okay, yeah. All right, so that is the acceleration. Now part E, I'm getting a little interesting. I want to know at what values of t does the particle change direction. Okay, let's consider a parabola. Okay, I go up and then I come down. Okay, and let's consider where I change direction. Here I have a positive instantaneous slope because I'm increasing. Okay, here I have a slope of 0 because it flattens out that tangent line. And then I'm decreasing. Oh, those are not decreasers. Oh, dang. Okay, sorry. Let's do some color coding here. Here I have a slope of 0. And then going down, I have slopes that are negative because I'm decreasing. So these little symbols represent the symbol of the instantaneous slope. So positive instantaneous slope, 0 instantaneous slope, negative instantaneous slope. Okay, so where do I change direction? I change direction right here. Okay, I change direction right there. So at that point, my instantaneous slope equals 0. Or, in this case, my velocity equals 0. All right? Because I have a slope that's positive, a slope that's 0, and a slope that's negative. Clearly, this is where I'm changing direction on my journey, and that is also where my velocity or my rate of change equals 0. If I'm driving in a car, okay, I'm driving and then I go the other way, my car actually stops momentarily. It has to stop because it then has to go the other way. So when my velocity is 0, that means I have changed direction. Okay, so, oh, also, what point is this on our parabola? It's our vertex. So we have these connections. The vertex of the parabola is where the velocity is 0, is where I change direction. Okay, so all those things are pretty synonymous. So I want to know, where does the function change direction? So, or I'm sorry, at what values of t? Well, v of t equals 2t minus 3. That's crazy t. And I want to know where that equals 0. So I can write 2t equals 3. Let's extend the page. This is harder than it looks, I promise you. Sorry, we'll start this over. Okay, so now I'm just solving an algebraic equation. I get 2t equals 3 and t equals 1.5 or 3/2 seconds. So because my slope of my tangent line is 0 where I change direction, that in Newtonian physics, so when we're talking about position, velocity, acceleration, it is where the velocity equals 0. Okay, part F, put that away, says where is the particle when S is at a minimum? So you want to find the minimum of S of t. And here's this function t squared minus 3t plus 2. Is it a minimum? Where? So let us consider this is an upward parabola. So the minimum is going to be at the what? The vertex. So did we find the point in time where this, sorry, I'm trying to scroll this down. There we go. Did we find over here the point in time where I was at my vertex? I sure did. I changed direction at 1.5 seconds. That is the vertex or the minimum. Ooh, crazy. Okay, let me fix that. Minimum. There we go. So that's the vertex. So I know my minimum occurs when t is 1.5 seconds. That's the when. I want to know the where. So I want to find out what is my position at 1.5 seconds. Okay, so let me just, this is supposed to be curvy. Curvy. All right, so S of 1.5 is 1.5 squared minus 3 times 1.5 plus 2. So this is 2.25 minus 4.5 plus 2. So this, I believe, is going to end up being negative 0.25 meters. So this particle gets as low as negative 0.25 on the number line. That's the lowest it gets in terms of its position. So that is how you find where the minimum is at. We found what time it changed direction, and if it's a parabola that's upright, the place that it changes direction is its vertex. Okay, so the big ideas for this particular chapter are that if you take the derivative of a position or a displacement or distance function, you get velocity, and if you take the derivative of velocity, you get acceleration. Also, another huge idea is this idea of changing direction. If you change direction, your velocity is 0. That is critical. And very exciting too, because you know what we just did? We found another way to find a vertex. You don't have to memorize negative b over 2a. You don't have to graph it. All we have to do is take the derivative, which is pretty easy with polynomial functions, set that derivative, that velocity equation equal to 0, and then we can find our vertex. All right. Any questions? You can ask Mr. Wozniak. Thank you, Mr. Wozniak. Your homework is, I'll write it in rainbow to make it less arduous. It is going to be on page, oh, it should be over here, page 129 through 131. And you're going to do problems 3, 5, 8, and 16. I crossed it out. So I'll put a star this time and say it's a challenging bonus one that I thought was too hard. But if you want to challenge yourself, right, you could do that. All right. Good luck on your work, and I will see you all tomorrow.